This is a webinar on quantitative optical gas imaging, also known as QOGI, and how it can be used for the detection and quantification of hydrocarbon gas leaks. In this webinar, we're going to go over why somebody would choose optical gas imaging, what optical gas imaging is, and how optical gas imaging is different than normal infrared. After that, we'll get into some of the QOGI side of the business. Optical gas imaging is a very unique technology that leverages an infrared camera and gives an operator abilities to actually see hydrocarbon and methane gas leaks. This leak detection technology allows them to improve safety and emissions mitigation metrics within their organization. By keeping gas in the pipelines, they can enhance productivity and improve their bottom line. They can lower capital and operational costs and reduce business risks by helping to meet any ESG goals within their organization. So why would you choose optical gas imaging? Simple, E squared. It is an effective and efficient technology to actually find leaks and now to measure them. You can find them fast and you can find them from a safe distance. And with optical gas imaging, you have a video, you have a visual evidence of those emissions, not only to document what's happening at your sites, but also to actually know where that leak's coming from, where the leak's going, and to ensure safe operations. In previous studies, optical gas imaging has proven to be up to 9 times faster than method 21 or sniffing technology, and is a high ROI for producers by keeping that gas in the pipelines and allows them to increase their bottom line. One way to show how optical gas imaging works and to make the invisible visible is with CO2. In this video taken from the Consumer Electronics Show, we use just a simple soda stream, fill it with CO2 without any water in it, turn it upside down, and show what gas looks like pouring out of an empty bottle. Another way to show how optical gas imaging works in your world are some common ideas, like a hand sanitizer or a residential leak in a front yard. On the video on the left, you'll notice a little hard to see the leak until FLIR's patented high sensitivity mode is activated, and it's easily be able to see the gas coming off of the chemicals in hand sanitizer. On the right, you'll see a fire truck, and you'll actually see a leak in a common residential neighborhood underneath the sidewalk. Another way to show OGI in your world are to show you some videos of a gas station. On the left, you'll simply see somebody filling their truck up with gas. Those fumes are the ones you may smell, but may not see. On the right, you'll see a lid from an underground tank and show the dangers of this in an environment where other vehicles may be passing right over the top of this. So how does optical gas imaging work? To put it simply, an infrared camera sees an object and makes an image. So that object emits energy, goes into the infrared camera, and creates an image of what's happening behind that. Most of the time, you have an image in the background and you have a gas plume in between the camera and that image that the camera is making from the background. When that happens, that gas plume actually absorbs some of the energy and blocks the energy from reaching the camera to create an image. And that's what we see as smoke in the infrared image or the optical gas imaging camera. If we look a little bit about the basics of the science behind optical gas imaging, we start with an electromagnetic spectrum. The infrared spectrum is the one just past a visible light spectrum, and generally speaking, there are two different bands of infrared, midwave and long wave. Most infrared cameras or optical gas imaging cameras are used in the midwave spectrum for hydrocarbon detection. That spectrum allows for a camera to see all hydrocarbon gases in a broad spectrum between 3.2 and 3.4 microns. There are some gases, like methane, that allow a camera that operates in a long wave spectrum to be used and makes it easy to see individual gases in certain scenarios. So how does it work? What we do with the camera is we match the spectral response of the camera to the peak spectral absorption of the gas of interest. In the graph on the right, you'll notice you have propane, benzene, methane, and ethylene, 4 gases that you may find in a hydrocarbon application in various industries. As we match the camera's spectral response, in other words, how the camera is maximized in the filter that we put in the camera, to the peak spectral absorption of all of these gases, we can see them. And generally speaking, most hydrocarbons will absorb some energy between 3.2 and 3.4 microns. But how do you tune an OGI camera? You do that through special filtering. And in our hydrocarbon cameras, which are cooled midwaves cameras, we actually put the filter inside the cold shield or the camera body. And what that does is allows the energy to come through the infrared lens and reach the camera body. At that point in time, it hits the spectral filter, which is filtered at 3.2 to 3.4 microns. That limits the amount of energy that gets through the spectral filter and hits the infrared detector. Now, because we're able to do that, we're able to block out certain scenarios in that previous example where the gas is present between the camera and a background image, and we can see the gas as smoke. What's unique about FLIR's cameras is that our spectral filter is built into the cold shield. This means that at any point in time you turn an infrared camera on or an optical gas imaging camera from FLIR, you know that the camera is operable and the camera will see a gas if present, as long as the camera creates an image. Some cameras in which the filter can be removed or changed may have a problem in you understanding and knowing if that filter is present or if you're using the right filter for the application of interest. To understand optical gas imaging cameras, you need to know that not all OGI cameras are the same. This shows you the portfolio that FLIR has in comparison with 4 common hydrocarbon gases. You'll notice that all of them have a spectral response in that 3.2 to 3.4 micron range we've discussed. But as you move into the long wave above 7 micron, you can see where methane has some absorption at 7.7, ethylene has a considerable amount of absorption between 10 and 11, but other common gases like propane and benzene, have little to no absorption in the long wave spectral. You also need to know that OGI cameras are not limited to just hydrocarbons. On this slide, we show the full portfolio and the various industrial gases that we can see. Methane, like a lot of other hydrocarbons, will have an absorption response around 3.2 to 3.4, but also has one around 7.7. Some other common gases in the world, like carbon dioxide, which has a response around 4.3, carbon monoxide, which is around 4.6, and some refrigerant gases, in this case R508A, which is right around 8, which fits into our G304 camera for refrigerants or hydrofluorocarbons from 8 to 8.6 micron. And another very common gas for us is sulfur hexafluoride, which is a common gas for insulating in the electrical transmission market, has a response factor that peaks around 10.6 micron. If you'd like to learn more about the optical gas imaging portfolio, the various gases we can see, and the various industries and applications in which optical gas imaging cameras from FLIR can be applied, please visit our website at flir.com/OGI. If you need more guidance on what gases you can see with FLIR OGI cameras, you can go to our website. This is an example of a chart showing the various cameras that we have, the gases that may be able to be seen with our cameras, and how well we can see them. And now that we've covered some of the basics of optical gas imaging, we can get into quantitative optical gas imaging, or QOGI. Here we're going to talk a little bit about the fundamentals, just to give you a basic understanding of the difference between QOGI and OGI itself. Some tips and tricks to help you in your QOGI world and to be able to get better results in the field. And we're going to show you how QOGI actually works with some validation studies in the market. So the fundamentals of quantitative optical gas imaging. So what is QOGI? Quantitative optical gas imaging is the ability to use a special engineered infrared camera or optical gas imaging camera that's made specifically for hydrocarbon detection, and you combine that with an algorithm specific to that technology, and it allows you to quantify invisible leaks that you cannot see with your naked eye. Why QOGI? Simple, you can see the leak, so you know where to measure the leak. With the TVA, you can see that if you don't know exactly where to point it, you may not be measuring anything at all, much less accurately or measuring the emission. In addition, you can inspect DTM, or difficult to measure or difficult to monitor components. This is a quick video showing you a component that's overhead and would be very challenging, if not impossible, to inspect and measure with other technologies. While QOGI as a technology is fairly new, this is the evolution of the QOGI technology from FLIR. In 2016, the first ever QOGI technology solution was launched by Providence Photonics, our solution partner. They launched the QL100, which was based on operation with a FLIR GF series camera. In 2017, they revamped that to make it a little bit easier to use and to align with some of the newer FLIR technology, including Q mode support, to allow operation in ATEX areas. After a more direct partnership with Providence, FLIR and Providence in 2020 launched the FLIR QL320, which is the baseline of the QOGI technology that's in the market today in a tablet. This added a number of features like the ability to measure concentration and some of the screening features which are critical to the use of the technology. Today, we have quantification in our G series portfolio of cameras. This is a streamlined QOGI application that has the same analytics that's been proven over the last 5 years. It gives you a basic infrared image output, just a JPEG image, with the QOGI data embedded, and there is a potential in the future for this to meet regulatory demands across the globe. As we talk about QOGI, you need to understand the optical gas imaging triangle. In general, there are 3 things that need to be present in order for an optical gas imaging camera to see an emission as well as quantify that emission. First, very simply put, there needs to be gas in the field of view or in the screen. If there's no gas present, you can't detect it and you can't quantify it. Next, the camera of interest needs to be engineered in such a way that it can visualize that gas. So that gas must be able to absorb energy within the filtered wavelength of the optical gas imaging camera. The last thing is delta T. There must be a sufficient temperature differential between the gas plume itself, which is assumed to be the ambient temperature where the gas comes out, and the background temperature behind the gas, which is what would be imaged by the optical gas imaging camera. So how much gas is present? This video is a good example of showing that intensity and how different amounts of gas would show differently in an OGI camera. On the left, you'll see a propane leak of around 2 liters per minute, and you can see the intensity of the emission on the right with a propane leak at 16 liters per minute. But you also need to understand the absorption coefficient that some people may refer to as response value or response factor of the camera. In the 3.2 to 3.4 micron range, in using the QOGI technology from FLIR, different gases have different RF or response factor values. In this video on the right, you may wonder which leak is bigger, propane or methane? Many may look at this and say that must be a bigger leak on the left because it's propane. Yet on the right, it's methane, which simply has a smaller response factor, about a third of what propane is. Both of these emissions are exactly the same in a laboratory environment. And you need to understand the effect of delta temperature. In this video, it's a good example of a high and good delta T on the left and a poor delta T on the right, where you have a wall on the left, and on the right you simply have a chain link fence and trees in the background. You'll notice that the leak seems to disappear unless you intensely look at the chain link fence where you can see the leak carrying over there. The leak didn't go away. What happened is there's poor delta T on the right where you simply have ambient trees in the background versus a warm wall. What is delta T? By definition, delta T is a temperature differential between the gas plume temperature, which is assumed to be ambient air, and the background temperature. In this image right here, you can see that we would subtract the ambient air temperature, or T2, from the temperature of the background that is taken with the radiometric capabilities of a FLIR camera, or T1. That subtraction will get you the delta T reading and ensure that you have enough delta T to be successful in your QOGI analysis. You also need to understand delta T in the various types of plumes that you may have. In some cases, delta T will be higher, which was usually an absorptive plume. What this means is the background is hotter than the ambient air temperature or the gas temperature. Generally, with a camera in white hot palette, like most OGI cameras are used in a black and white scale, that's actually going to show a black plume. There are times in which the plume would be emissive, and what this means is that the plume is emitting energy rather than absorbing energy when you have a hot background. The most common type for this is with a sky background. As you can see on the image on the right, a cold sky is colder than the plume or the ambient air temperature, in which case this will show as a white plume compared to the background. This is also known as an emissive plume, and in the technology or the QOGI technology, we simplify it, just asking you to tell us what color plume you have. So, how do you use QOGI? There are 3 ways to use FLIR's QOGI technology. The first is tethered or connected, where you have a QL320 directly connected to a camera via USB cable. This is the most advanced way to use the QOGI technology from FLIR and gives you the most advanced features with live recording, as well as some unique features like masking that's built into the QL320 but not into QOGI and camera. The second is via Q mode with a G or a GF series camera from FLIR. In this case, you record a file or a video on the camera itself, and you can post-process that on the QL320 to activate some of those advanced features like masking. This is quite common in an ATEX environment where you cannot connect the camera to a QL320 live. The newest feature from FLIR related to QOGI is quantification in camera with the new G series camera. In this case, you simply set the camera up, you set the parameters, and record for 10 seconds with an output simply being a JPEG image. So when do you use each mode? Why would we still have a QL320 if we have quantification in camera? There are scenarios where a QL320 gives you some advantage. One of those is accuracy. You may want the most accurate results, and you need a longer recording to be able to get the most accurate results using a QOGI technology. You may also have flexibility needs. In that case, you may need to use the masking feature or other advanced features within the QL320 that give you more opportunities to have accuracy within your QOGI technology. If you need simplicity or speed, in other words, if the goal is to simply go out and use an advanced QOGI analytic and an advanced QOGI technology and get a result after around 10 seconds, the QOGI in camera feature is going to be the feature for you. This will give you a confident result, but the ability to mask out other features, as an example, will not be available in the in-camera feature. And if you need to use your camera in an ATEX or a Class 1 Division 2 environment, you would not be able to use the QL320 tethered to an OGI camera from FLIR. So when would you use Q mode? As we discussed, the most common application for Q mode is in ATEX areas. But a lot of customers simply like to use this for convenience. If you have a legacy GF series camera and you simply don't want to tether a tablet to the camera and you want to be able to analyze and post-process that data after the fact, you can use Q mode. But you want to ensure when you're using Q mode, you set the user data appropriately and apply the temperature screening methods built into the Q mode feature to ensure the most high quality data that you can. Now, let's look at the QL320. How does it work and what features are involved? If you're using the QL320, you will have a variety of user inputs. These are also available in the Q mode feature, in the GF series and G series cameras, as well in QOGI in camera with the new G series camera. You do have masking features in the QL320 which are available either tethered or for use in the Q mode processing or post-processing feature of the QL320. The overlays show on the actual QL320 screen itself. You have 3 different overlays. One of those is delta T, showing where you may have insufficient delta T, which is a critical feature and also available in both QOGI in camera and the Q mode features of the camera. There are various units that you can use, from the distance to the temperature and to whether you have variety of flow or concentration measurements needed for your QOGI technology application. The different modes are going to allow you a normal or expert mode. It also gives you a demo mode, which allows you the capabilities to experiment with various leaks, and the load mode, which is the one on top, which gives you the capability to load a Q mode video for post-processing. As mentioned, the demo mode allows you for training and for other purposes to be able to experiment with the QL320 and the QOGI process. When you're using the QL320 tethered or with the Q mode feature, you do have the capabilities to manually adjust the plume intensity. Most often that's not needed because we optimize any recording and any use of the QL320 with what seemingly is the best plume intensity versus a manual plume. But there are some scenarios where this can be beneficial. You can measure and rerun any analytic or any Q mode feature or Q mode video so that you can get the most appropriate data after you change some of the parameters. It will give you a simple results display and even a loading bar so you know how far along in your Q mode evaluation you are. You have a dialog box which gives you the capabilities to do some some unique analysis and to know the previous runs that you've done within your QL320. And a new feature in the QL320 is the image stabilization feature. This is if you're using a FLIR OGI camera and you want to quantify an emission in which you were not able to use a tripod, but you could keep the camera very steady and be able to analyze a image that has slight movement. So we do have some updates within our QL320, and this is in version 1.5 that was released in the summer of 2024. The first of that is a high emitter calibration. Historically, the QOGI solution from FLIR had a maximum calibrated range of around 12 kilograms an hour. The new high emitter calibration allows the use of the technology at calibration range up to 500 kilograms per hour and extends the working distance for these high emitting events out to around 120 meters. This does have the potential to meet future regulations as it relates to super emitter calibration and also allow operators the ability to measure an event to ensure that it is under any super emitter regulatory requirement. A new feature is that it is compliant with the G series camera from FLIR. The GX320, the GX620, and the G620 cameras all work now with the QL320 both in tethered and in post-processing mode. It does give you a concentration measurement now in parts per million versus simply parts per million meter. And what this means is you can meet any requirements, like in Mexico, where you need to measure in parts per million. If we look at the super emitter leak calibration, this is a huge advantage to the camera. This allows an operator or a user to look at an emission and understand its intensity when it was outside of the previous calibration curve of the QOGI solution. This changes dramatically the amount of capabilities of the QOGI detection in both the flow measurement as well as the distance to use the technology. But a really revolutionary feature is the new image stabilization feature and an image stabilization option within the QL320. This can be used either live and tethered, or it can be used to post-process a Q mode video from a GF series or a new G series camera in which utilizing a tripod may be challenging or difficult. This can be toggled on and off in the GUI of the QL320. It can be used in various applications, but it is highly recommended to keep the camera very steady, as stable as possible. Minor movement will be compensated, but if you get too much movement, you will be shown an error and the recording will be restarted. Of course, a tripod is always going to produce the best results with the QOGI technology, but a monopod can be recommended in various applications, but a handheld operation must be as stable as possible. And when you're using stabilization, you want to ensure that it can help with scenarios where there may be something in the image causing issues like a pipe or a rooftop, because it'll help stabilize that scenario. One way to show the stabilization feature is to show it on our legacy algorithm compared to our new advanced algorithm. On the video on the left, you'll see as we turn on the plume overlay, it's colorizing the tank and the buildings. This is because as your handheld operation using the camera, it sees those pixel movement quite dramatically in the camera. Compare that to our new advanced algorithm with stabilization. Now the plume colorization only focuses on the plume because we are focusing out or eliminating the pieces of movement that are not plume related as we add the stabilization feature into the technology. In another example, this is not quite as dramatic in the sense that You can see a emission coming from a tank. This is a small emission coming from a vent pipe. In this case, there's a lot of items touching the ring. That's the measurement piece of the QOGI technology. But as we use the camera and we stabilize it with the stabilization feature within the QL320, we change the result from 6,500 standard liters per minute to 11 standard liters per minute, which is a more accurate reading in this application. One of the most common applications that we may envision utilizing the stabilization feature is when you're on a catwalk. Sometimes it's challenging to get a tripod carried up to the top of a catwalk and even to get it applied and used. In this case, on the video on the right, you can see a very minimal movement with a handheld operation and an image on the left utilizing the tripod feature. When we applied the stabilization metrics within the QL320, we changed the result from 500 standard cubic foot per hour to 200 standard cubic foot per hour. The newest feature in QOGI with the FLIR portfolio of cameras is the new quantification in-camera capabilities. With this, you'll need to use a camera on a tripod as stabilization hasn't been added inside the camera at this time. This is an example in a scenario of quantifying a general BIC or a butane lighter. In this scenario, I simply turn the camera on, choose the mode, and select quantification. Now I need to go in and set the appropriate parameters, like the ambient air temperature, so that I can ensure appropriate delta T, the wind speed from low, normal, or high. I want to set the leak type, which is point diffused, get the right distance from the leak, what type of gas it is, in this case it's a butane lighter, and is the plume black or white. You can measure in flow or concentration, set a delta T overlay, which I always recommend, and when you're ready, you go back, hit the arrow, and you start your measurement so that you can do this. You hit got it, and then it will count down from 5 and begin measuring. Once it starts its measurement process, which takes about 10 seconds, the plume will get colorized. Now it's looking at the emission from the center of the plume, and as it reaches the plume and moves to the outside of the plume. At the end of the 10-second measurement, you'll see a very brief visual picture and then an option to view summary. This gives you the capability to make sure that your input parameters were done correctly and also gives you a quick view of the reading that you got. In this case, 15 grams per hour from a general butane lighter. So here are the top 10 tips and tricks for QOGI success with the FLIR QL320 or FLIR QOGI camera. The first tip in using QOGI technology is to remove foreign objects. You want to make sure if there's something in your image that's moving around, like an LDAR tag or maybe a ribbon that's tied onto a leaking component to show where it is. You want to make sure that those components or those items are removed in the video. When you're using QOGI and OGI itself, those components move around inside the video and the technology may see that as an emission. In this case, you'll see an LDAR tag move from the center of the boundary and then cross the boundary as it's moving with the wind. With the technology, that may assume it's an emission and include that in the analytics. Here's a video example of that image you just saw. Here you can see that the LDAR tag is moving in the wind, and the technology sees it and doesn't know that it's an LDAR tag and simply thinks it's a large block of an emission moving from inside the measurement boundary to outside. The second tip is that stability is a must. Even with the new QOGI stabilization feature in the QL320, you want to ensure that the video you have is as stable as possible. With QOGI and camera, you do need to use your OGI camera on a tripod to get the best results. With the new stabilization feature, whether you use a monopod, a tripod, or even handheld, you need to ensure that the camera is as still as possible. While stabilization is critical in the success of QOGI, the new QL320 image stabilization feature does make this easier. Here's another example comparing the legacy QOGI algorithm with the new advanced QOGI algorithm enabling image stabilization. In our third tip, delta T matters a lot. As we've discussed throughout this presentation, the use of a delta T feature or ensuring proper delta T with QOGI is a must. It doesn't have to be a lot of delta T, but a little bit of a difference can change the output. Generally, we recommend at least 2 degrees Celsius in delta T, which you can put into the delta T overlay feature and ensure by visually looking at the image whether or not you have sufficient delta T in your OGI camera. To show an example of delta T, this is a video from a testing lab out in the field. The actual leak rate in this emission was 32 liters per minute. Using the camera with the correct delta T, we had a 34 liter per minute reading. As we changed the delta T in the technology by just a couple of degrees, you can see that our emission was off up to 45 liters per minute. This just shows the importance of delta T and how it does have an effect on the outcome and on the reading itself. Another tip in using QOGI from FLIR is to try and center the leak. You would want to do this especially in the flow measurements, and it's not as important in concentration measurements. Using the technology, you want to try to center where the leak is exiting from any component and put that in the middle of the blue circle. This helps us ensure better accuracy as the emission travels throughout the blue circle and then across the boundary so that we can have increased accuracy in using our QOGI technology. All of the QOGI technology requires parameters that are put in by the user. Like the old adage goes, good data in equals good data out. When you're using the technology in the field, whether it's QL320, the QOGI in camera, or the Q mode feature, try to make sure that whatever data you put in is as accurate as possible. The better the data in, the better the data out. Another good tip in using the QOGI technology is that when a leak is so small that it can only be imaged using FLIR's patented high sensitivity mode, it may not be an optimal leak to be quantified using our QOGI technology. There are also environmental conditions to take into account when using QOGI technology. One of those is the wind. When you're using your OGI camera, in particular using your OGI camera for quantitative optical gas imaging, you want to ensure that you don't look at the image when the leak is either moving directly towards or away from the user. Try to look at the image when the leak is moving perpendicular or to the side of where the user is facing the leak or the component that is leaking from. In some cases, too much wind can cause the leak to move too fast to quantify. In other cases, there may be a scenario where there is not enough wind to cause the leak to move from inside the circle to outside the circle. This is often called pooling, where the leak pools up or stays inside the circle, and it becomes challenging because the full emission does not move from the inside of the measurement boundary to the blue ring where the technology measures the emission. There can be some limitations to QOGI technology. As we've discussed throughout the presentation, delta T is a must, and you want to have a delta T of 2 degrees Celsius or greater. Another potential limitation is the leak detection. Historically, and with the legacy QOGI technology, we could measure from 11 grams per hour up to around 12 kilograms per hour. Now with the new super emitter or the new high volume emitter calibration curve, we can measure up to around 2,000 kilograms per hour. Distance-wise, historically, we could get out to around 210 feet, but now with the high emitter or the high volume emission super emitter curve, we can get out to around 1,000 feet and be able to measure with our QOGI technology in the QL320. You also need to understand the conditions in which you may be using the technology. In this example, we tested the equipment and the technology out in the field when we had slow-moving clouds in the background. We fully expected this result, but we're showing here how challenging it is to use QOGI technology with slow-moving clouds in the background. In this case, you would want to get a better view or a vantage point where you either have a clear sky or you need to have a top-down view where clouds would not be in the background in using the QOGI technology. You also want to be aware of external leaks. There are scenarios where you may have emissions from a secondary source that flow and move into the measurement boundaries of a desired measured source. In this case, you can see exhaust emissions floating in to the desired measurement ring. There are various validation studies that are out in public related to the QOGI technology, and we're going to go over those now. One of the most basic and one of the oldest validation studies was one of the first ones done of the QOGI technology. In this case, we utilized the original QOGI solution, the QL100, and we compared it to a TVA or a sniffer. This was performed in Europe at Vito, a renowned test facility, and there were a number of different gases quantified, and there were 21 scenarios tested. What were the results? Compared to a TVA or a method 21 solution, the average difference, or the average difference between the calculated emission and the known release for a QOGI solution was 6%. The average difference for a method 21 was 31%. As you can see, the QOGI solution performed more than 5 times better than method 21 in this testing environment. Another great study is the Alberta Methane Field Challenge, or AMFC study, that was in June of 2020. This was a third party of both academia and various organizations in Canada that wanted to test variety of methane and hydrocarbon detection technologies and utilize the QL320 as the baseline for testing. There were approximately 100 tests in this study. Some of the key insights is that QOGI technology is a very good technology and provides comprehensive estimates of aggregate methane emissions. What does that mean? On an individual measurement basis, on a single measurement for QOGI, it can have a wide variance of error. But as you begin to use the technology in aggregate, or the more measurements you have, the better the results. In other words, 10 measurements on average is better than 1. Averaging 100 measurements is better than 10. So what this means to an operator is that on an individual measurement baseline, they may have some percentage of error, but the more measurements that they have, the more accurate their overall emissions. Maybe this means they would have an average of various measurements at a single site, in a single region, or over time, like measurements per week or measurements per month. The more data inputs you have, the more accurate those results would be. FLIR went to METEC, the Methane Emissions Testing Evaluation Center at Colorado State University, and we wanted to try to validate the AMFC report. In this case, we actually had a METEC staff that was operating the various emissions, and we went out and tried to measure all of these emissions with the Q mode technology of FLIR. Our results were very similar, with the exception of known and expected negative results. We did confirm the challenges of cloud issues. You'll notice the great percentage of error when we have clouds directly behind a known emission source. So we knew that this would happen, and we were able to validate this. If we exclude the cloud readings and we take the average of all of the readings, we were only off by 4% aggregate compared to the actual leaks that were established by the METEC staff. Similar to the Alberta Methane Field Challenge, there were some leak measurements where we were off high, and there were some leak measurements that we were off low. This is a great validation study of the Alberta Methane Field Challenge and the accuracy of QOGI technology in an aggregate setting. Another study that focused on QOGI and measurement technologies was the study by the European Gas Research Group. This study had a very minimal number of releases compared to some previous studies with only 17 blind releases. It did have a wide array of release rates, and many of those being outside of the existing calibration range of the FLIR QL320 solution, and there were 2 QOGI technologies evaluated in this study. With the 2 OGI cameras that were evaluated and QOGI technologies that were included in this study, both of those had underestimated the emissions, which is common in most studies related to QOGI and optical gas imaging. In the study, OGI camera number 1, which was not FLIR, but another manufacturer, performed better according to the study's words, but as you research the study, they had a very high level of uncertainty, which potentially could mean that the image or the data was adjusted by the camera operator. In this study, the camera was operated by one of the manufacturer's engineers rather than just a field operator like would be common in the field and as a true user of an OGI camera. Looking at OGI camera number 2 in the study, which was the FLIR GF320 used with a FLIR QL320, the level of uncertainty was 0, which simply shows that the operator of the technology took the reading and moved on. This study was performed by a FLIR customer rather than an engineer from FLIR or one of the scientists behind the actual technology. Another thing to point out in the study is that the majority of the emissions where we had a high percentage of error were outside of our calibration range of 11.8 kilograms per hour. This study was performed with the technology before we had our new high emitter calibration range. Another new study is the METEC QOGI study, in which they did a wide variety of measurements, 357, utilizing FLIR technology, ranging from 2 to 88 liters per minute in release rates. Some of the thing is the error increase with larger release rates, which is expected within the technology. In this study, they had 2 operators of the technology. One had a certification training, the other one did not, related to the operation of the OGI camera from FLIR and the QL320 technology. They did try to get 3 camera positions per leak, and one of the goals of the study was to test 4 key parameters related to QOGI: the emission rate, the plume background, the wind speed, and the measurement distance. One of the results of this study was that it was the first QOGI study that overestimated emissions. In this case, the study had an overestimation of 43% in an aggregate setting. The delta T is a bit of a concern as we review this study. because temperature is a critical factor in there. Nowhere in the study did they reference utilizing the delta T plume overlay, which is added into the QL320 and the QOGI in camera to make sure that we ensure the best results within the technology. In looking at the results from the study, and in particular the 4 tested parameters, some of them were as expected and some were a little bit surprising. Taking into consideration emission rate, it's not surprising that the higher emissions are easier and have better results than a lower emission or a very small leak, which is challenging because it's easier to have a larger percentage of error with a very small leak. Looking at the wind speed, it's not surprising that a calmer day would produce better results than a scenario where you would have higher wind speeds. What is a bit challenging or a bit surprising is the plume background results. In this study, they stated that the equipment background had the worst results. That's a bit different than the previous studies that we've seen, because most of the true QOGI analysis or the studies that we've seen were real-world examples, where equipment that's in the background would have process heat and allow for a better and higher delta T in the results. And it also doesn't surprise us that a clear sky would produce very good results. If considering the measurement distance, the medium or the middle measurement at 2 to 10 meters produced the best results. If you're very close up and very close to the emission, sometimes the results can be more challenging as the leak is moving faster and at a quicker distance inside the measurement boundary. In looking at the study, there were also a few outliers that would have a dramatic effect on the overall results. As you can see in this graph, there were 3 outliers that would have an extreme effect on the overall results of QOGI as a technology. These 3 outliers were not detailed as to why they were such heavy outliers in the study. Delta T was not mentioned in the study as it is a critical factor in the success of quantitative optical gas imaging. And as we looked at some of the results when they used equipment, that had the largest sample count of 149 and the best percentage within a factor of 2. This contradicts their statement that equipment would have the highest error or the worst results in accuracy, but also confirms previous studies like the Alberta Methane Field Challenge and FLIR study at METEC, in which the higher sample count that you have or the more readings that you get, the better the results. If you're interested in learning more about quantitative optical gas imaging and attending an on-demand, self-paced learning on quantitative optical gas imaging and the use of a QL320 tablet, you can go to our Infrared Training Center website at infraredtraining.com and find this training under the optical gas imaging training options. Thank you for participating in this presentation. If you have any questions, please reach out to your local FLIR representative and let us know if we can help you.